Hey guys, sorry. So today we're doing our intro to calculus. So I thought I'd just start with a quick how did calculus come about question. So there's two geometric problems that led to the development of calculus. So if you haven't heard this yet or seen it in your textbook or online, the two problems were basically finding the rate of change at one point. So tangent lines was the first thing that led to the development of calculus. So like people wanted to know what is the slope of a tangent to the graph of a function at a specific point. So if we had a crazy graph and we wanted to know what's the slope right here, what's the slope of that line, we needed a way to calculate that. And that's basically our focus this semester. And then the second problem that people wanted to figure out was about the area under a curve. So basically, if you took that same graph and you wanted to figure out, I want to know what the area is under the curve between these 2 points. Like, I want to know what this area is. Those two questions brought about calculus. And in this class, we're going to focus 100% on this. And the area under the curve part is going to be what you learn in university. So we're going to be using our main thing that we're learning this year is about derivatives, as they're going to help us find the instantaneous rate of change at one point. So that's basically our whole semester right there. Figuring this out, understanding it, learning derivatives of each type of function, and applying those concepts. This area under a curve thing is called integration, and we're not learning that in high school at all. So you can think a bunch of famous mathematicians like Archimedes, Fermat, and then finally Newton and Leibniz for their contributions to calculus. All right, so just a quick overview of what we're doing. We're going to start with the last thing you should have learned in advanced functions, but a lot of times teachers don't get to it. But it's also something you learn in grade 9 math, and that is called rate of change, also known as slope. So we're going to talk about rate of change, and we're going to talk about the rate of change as an average rate of change between 2 points, and we're also going to talk about it in terms of an instantaneous rate of change, so at one point. And this guy right here is going to lead us to tangent lines and derivatives. So rate of change is our first topic, and that's going to be our goal for this week of math. We definitely want to understand rate of change, average rate of change, and instantaneous rates of change. And maybe somewhat get some skills practice out of the way too. So you definitely want to understand this week because the whole entire calculus course is based on understanding rate of change. So that's for this week. Then we're going to head into next week. We're going to do limits. We're going to talk about what the heck those are, how they apply to rate of change and instantaneous rates of change, and then that's going to bring us to derivatives, which we'll probably cover next week as well. And then we're just going to go on and apply it and learn about different rules. Okay, so let's talk about, this is like almost like a grade 9 video. Let's actually just talk about average rates of change. Average rate of change. Okay, so for our average rate of change, let's take a graph that looks like this with a line, or a curve, sorry, that looks like that. And let's just draw 2 points on our curve. And we want to figure out what the rate of change is between point P and point Q. We want to know what is the rate of change. What's the average rate of change? This is a curve, which I'm actually just going to redraw because it looks Messy. Oof. I'm gonna redraw all of this. I'm sorry. I just definitely want to make it look there, like more of a curve. Okay, so we got a point down here, P, and a point up here, Q. So if we're gonna try to find the average rate of change right there, we could take a line that goes right through points P and Q. Just gonna make it go right through those points. Okay, there we go. So we can take a line, and we would call this line, a line that goes through 2 points, we would call that line a secant. That's the name of it, secant. So it's just a line that goes through 2 points. And that's how we would find the average rate of change between 2 points. And how we would calculate the rate of change is just like how you learned in grade 9. It would be like the change in y divided by the change in x. Otherwise known as y2 minus y1 over x2 minus x1. Which we could also write as f of x2 minus f of x1 over x2 minus x1. Because you know how we write y as, we can write that as f of x instead. Okay, so that's the average rate of change. That's how we calculate it. It's just slope, rise over run. Change in y over change in x. Like that's seriously from grade 9. Okay, versus, let's say we wanted to find the instantaneous rate of change. We've never learned that. Hi! So the instantaneous rate of change is the rate of change at 1 point on the graph. So that would be, like, let's say we took this exact graph that I already drew, but let's just say we wanted to find the instantaneous rate of change at point P. So we would actually draw, instead of a secant, we would draw a tangent line to the curve. So instantaneous rate of change is found by using a tangent to the curve, whereas average rate of change is found using a secant. So these two terms are very important, secant and tangent. So I'm just going to repeat that again. Secant for average rate of change, and tangent is at the instantaneous rate of change. Okay, let's do an example. It's somebody's birthday party, and they're filling up a bunch of helium balloons. So we're going to fill up these balloons, and we're going to check what the volume of these balloons are in cubic centimeters. So let's say we put air in the balloons every 3 seconds. Check it out. We collected all this data filling up balloons. If you're on a computer right now on an iPad, you could try desmosing this data and check out what the graph would look like. Especially if you're bored watching me write all this stuff. Okay. 0.0, 3,000. Okay, there's all of our data for these helium balloons. Okay, so in terms of variables, we can tell that we've got time and we've got volume. So if we were going to draw a graph of this information, which one would be our dependent variable? That would be volume. Because volume is dependent on time. So as the time increases, the volume of the balloons increase. Because we're filling it up every 3 seconds. So volume is our dependent variable. And T is our independent variable. And our graph is going to look something like, I mean, I'm not putting any numbers on it, starting at 0, 0. It's going to be some kind of exponential graph. Okay, so if we wanted to find the rate of change, we would be expressing it as our change in volume divided by our change in time. Another way to say that would be, we're expressing, like, volume is expressed with respect to time. So I'm just giving you that terminology because it's going to come up again when we start calculus and doing derivatives. So volume is our dependent variable, time is our independent. So rate of change is volume is expressed with respect to t, or another way to write that is v over t, or like change in volume divided by change in time. Okay, so if we were going to find the average rate of increase, let's say we're looking near the end of our graph. Like let's just say that's 30 seconds or something. Does that even make it? Let's just back that up a little bit. That's 30. This is like a very inaccurate graph here. 21, 24, 27. Let's just say, I'm not graphing everything, but let's just say we want to find the average rate of change between maybe 21 and 30 seconds. So we're finding the slope of the secant between those 2 points. Okay, so if we wanted to find the rate of change, let's do it in the interval from 21 to 30 seconds. That's our t values. So we want to find the average rate of change. So we're doing change in volume divided by change in time. Okay, so the volume at 21 seconds is, oh, let's do 30 minus 21. So volume at 30 seconds is, 4186.7 minus the volume at 21 seconds is 1436 divided by 30 minus 21, and we get approximately 306. And the units for that would be centimeters cubed per second. So that's the rate at which we're filling up this balloon. So that's the average rate that's happening between these 2 points. Okay, let's reduce that interval. Let's check out the interval between 21 and 27. So if you do the same calculations, change in volume divided by change in time. So you do like exactly what I did up there. So you take, 3052.1 minus 1436. So let's do it. Minus 1436. And then now on the denominator we'll have 27 minus 21. We're going to get approximately 269 centimeters cubed per second. And then if I did it again, but did 21 to 24 seconds, so I'm just trying average rate of change. So change in volume divided by change in time. I'm not going to show my work for this one, but I'll get roughly 236 centimeters cubed per second. So I'm kind of getting like closer and closer intervals to 21. So I'm finding like this rate of change, then this rate of change, then this rate of change. So my lines are all getting slightly less steep. It's kind of a rough drawing there. So I've tried all of those average rates of change. So I've gotten these different ones. So like, what if I wanted to approximate the rate of change only at 21 seconds? Like I want to know specifically, what is the rate of change going to be right at 21 seconds? Well, in that case, I would need to use a tangent line. So for the average rate of changes, I've been just using can't seem to move my paper. Okay, I've frozen my screen. I'm gonna open it back up again. There we go. Okay, so I've been using secants for these just to get the average rate of change between 2 points. But let's say I want to know what is my instantaneous rate of change? Instantaneous rate of change at 21 seconds. It's like totally impossible for me to just use 1 point to figure out rate of change. So I'm gonna have to actually draw a tangent line to my curve and figure out the rate of change. So I would actually have to, sorry, I'm just gonna redraw this tangent line because it's not really that good. I would definitely need to open up open up Desmos, draw a tangent line to my curve, get 2 points on my line, like pick another point down here that's on my tangent line, and then I would have to determine the slope. So that would be tough. So like, let's just say I did that. I opened up Desmos, I drew a tangent line to my curve, or you graphed this super accurately on a graph and you drew your own tangent line. I did that, and I got, when I did this calculation, 208 centimeters cubed per second. So if you want to open up Desmos and try graphing this data and draw on your own tangent line, or if you want to try graphing it by hand even, and then all you have to do is sketch a tangent line as good as you can with a ruler, pick another random point on your graph, and then just do the exact same thing. Calculate your change in X over your change in Y, and see if you get roughly 208 centimeters cubed. So as you can see, like as we brought our interval closer and closer to 21, like this is like 9 seconds apart. Then our interval got closer and closer till it was only 3 seconds apart. Like what do you think would give an even better approximation? Like the closer and closer we got to 21. So these are the two closest values we had, 21 and 24. Unless I use the graph to try to find a point that's closer, I don't really have an option. That's as close as I can get to the instantaneous rate of change, unless I were to actually graph it myself and draw a tangent line, pick another point, because you always need 2 points to calculate slope. So there you go. We approximated the instantaneous rate of change. So we're noticing like some really important things to highlight here are, as the interval gets smaller, so as our interval gets smaller, so like if we have a graph with a line and we're trying to figure out the slope at this point, if we pick far away values to find the rate of change, not as accurate as when we pick points that are very close together. So as your interval gets smaller, it gets closer to the slope of the tangent. At that point. So average rate of change should be pretty easy to calculate for you. It's just change in Y over change in X. So you definitely want to make sure you know how to calculate average rate of change. And even if you didn't get a graph, which we're not really going to work with graphs too much, so even if you got an equation like Y equals X squared, and you wanted to know the average rate of change. So we know what that graph looks like. Graph that 100 times. A parabola looks like that. So if I wanted to know what's the average rate of change, between X equals 2 and X equals 3. So if I want to know that, so what's the average rate of change between X equals 2 and X equals 3? All I'm going to do is figure out my Y value at those points. So Y would be equal to, you know what, I'm going to write this as f of X. So f of 2 would be equal to 2 squared, which is 4. So I know I'll have a point at 2, 4. And then if I check what f of 3 is, that's 3 squared, which is 9. So I'll also have a point at 3, 9. So this is just a little bit of work to figure out our X and Y values. So now if I want to figure out my average rate of change between 2 and 3, then I can do subtract my Y values, so 9 minus 4, and subtract my X values, 3 minus 2, so I will get 5 over 1, so just 5. That would be my average rate of change between those 2 points. And if I really wanted to get a close approximation to, say, the instantaneous rate of change at 2. I could pick values that are super close together. So I could say, what if I want to know, like, what is the exact slope right there? Well, I know right at 2. I know 2, 4 is that point. So if I wanted to pick a value that's really close, I could pick something like what's a value that's super close to 2? How about 2.0001? So if now I sub in 2.0001 squared, I get 4.0004. So now I've got another point at 2.0001 and 4.0004. So now if I want to calculate the rate of change between 2 points, I got 4.0004 minus 4 over 2.0001 minus 2. Let's just do that math. Oh, should I know that? 2.0004? And we'll add equal. You guessed it. So that's like approximating the instantaneous rate of change right at that point. So, and that's like an extremely good approximation. So it turns out, almost done here, to summarize, average rate of change is good for finding an average rate of change, as it states, by just using our slope formula, change in y over change in x. But if we really want to get an accurate slope at a specific point, then we're kind of using the exact same formula for average rate of change, but we're just picking a really small interval. So to get a good picture of like an instantaneous rate of change, the smaller the interval, the better. So that's our goal, finding the instantaneous rate of change at a point. And we're seeing that if we really want to know the slope at that point, then our skill set right now is to pick a point really close to it and find the rate of change at that point, because it's really close to the slope of the tangent. So basically, yeah, if you haven't figured it out yet, our end goal is to take any function and be able to find the slope at one point, which we haven't been able to do yet in math because we haven't learned about tangent lines. So these tangent lines are going to help us find the slope. So no matter what your crazy line looks like, you can find the slope at any point on it. The slope right there, the slope right here, the slope right here. And right now we can do that by using kind of like an average rate of change.